Hey guys, the objective of this video is to go through conditional probability, and then afterwards we're going to look at independent events. Okay, so let's start with conditional probability. So suppose that we had two events. Event A is an outcome of one experiment, and event B is an outcome of a different experiment. So then P of BA, so this notation here, is equal to the probability of B occurring given that A has already occurred. So that here is basically equal to the probability of B intersection A over the probability of A from occurring. So that basically means that the event B and A are dependent on each other. Okay, so the occurrence of one event has an effect on the probability of another event from occurring. So this is what this formula means. Okay, so P of BA is equal to the probability of B from occurring given that A has already occurred. So a good way to understand this is to look at an example. So let's say we had two events. So they're known to have the following probability. So probability of A from occurring is 0.6, probability of event B from occurring is 0.4, and probability of A union B is equal to 0.8. So we need to find the conditional probability of A given that B has already occurred. So P of A, B. So this notation here is called a conditional probability. Okay, so this means the probability of A given that B has already occurred. So to find this, we need to start with the addition rule. So this is something that we talked about in the last video. Okay, this here. So the reason why we need to use this is because, remember, the conditional probability, okay, is dependent on the intersection, the probability of the intersection. And so this is what the addition rule has. Okay, so what we need to do is find the probability of A intersection B by rearranging it. So we need to rearrange this formula here, making this the subject, which is what I've done here. So probability of A and probability of B and probability of A union B is already given in the question. So that's here. So all we need to do now is just sub in the numbers into the formula. So that's equal to 0.6 plus 0.4 minus 0.8. So therefore the probability of A intersection B is equal to 0.2. And so now using our conditional probability formula, okay, so probability of A, assuming that B has already occurred, is equal to probability of A intersection B, which is what we have here, over the probability of B, which is what we have in the question. Okay, 0.4. So that's equal to 0.2 over 0.4, and that's equal to 0.5, and that's half. Okay, so what that means is that the probability of A occurring, given that B has already occurred, is half. So let's move on to another topic, which is independent events. So two events. Let's say we have two events, A and B. And so they're independent if the occurrence of one event has no impact on the probability of the other event. So what that means is that the probability of B, given that A already has occurred, is just equal to the probability of B itself. Okay, so A has no effect on B. And same thing here, the probability of A, given that B has already occurred, is just equal to probability of A itself. So we can then use our formula from the beginning. So this is what we have from the beginning. So using this formula here, the conditional probability formula. So we said that P of B is equal to P of BA. This is what I have here. And since P of BA is equal to the P of B intersection A over P of A, so we have something like this. Okay, that looks like this. So now we rearranged, okay, these two sides to get something like this, where the probability of A intersection B is equal to the probability of A times the probability of B. And that can only happen if we assume that A and B are independent. Okay, so that was what we assumed from the beginning, that independence has occurred in our events. Okay, so A and B are independent. So let's look at an example. So again, let's say we are flipping 3 coins and we want to achieve 3 heads, and we want to look at the probability of 3 heads in a coin. So after flipping the coins 3 times. So we let C be H1, H2, H3. So H1 being the heads in the first turn, H2 being heads in the second turn, and H3 being the head on our third flip. So our aim is to find P of C, okay? So that means we have to separate our set into A1 being heads in the first turn, A2 being heads in the second turn, and A3 being heads in the third turn. So we know that flipping a coin and achieving heads is equal to a half, okay? So when you normally flip a coin, there's only heads and tails. So the probability of getting a head in just one turn is just half. And that's what this is, okay? Or in each turn, just one turn. And that's equal to half. So now, P of C, which is equal to the intersection of A1, A2, A3. So using our formula, okay, of independence, because they're all independent events, okay, that's equal to probability A1 times probability A2 plus times probability A3, okay? So the reason why these are independent is because when you flip the coin once, okay, that will give you a certain probability. And so now when A1 has occurred, when you flip the second time, okay, the first time has nothing to do with with flipping the coin in the second time. Okay, the probability will still be the same, okay, through each turn. So this is why we can use this multiplication rule here. So again, because there were the probability of A1, probability of A2, and probability of A3 was half, that means that that's equal to half times half times half. That's equal to 1 in 8. Okay? So what this means is that the probability of getting heads on the first turn and heads on the second turn and getting heads on the third turn is 1 in 8. Okay? Alright guys, see you in the next video.